All right, so last time we were in the middle of section 2.2, and we're going to pick up where we left off, and we're going to use the graphing calculator to solve a problem on a company that has fixed costs and variable costs. Okay, and it'll make more sense, I think, as I show you the question. So this particular company has a fixed cost of $200,000. That's like maybe that's like a fee they pay monthly to rent the warehouse where they store their shirts or something. Okay, but it's just they pay that one time per month, $200,000. But then they have a variable cost of $1.50 per shirt. Okay, they're going to pay that cost for every shirt that they make. So it's not just a one-time fee of $1.50. So it costs them $1.50 to make the shirt. They're going to sell it for $4. So what we're going to do is we're going to find a graph of the company's costs, which is money that they spend, and the company's revenue, which is any money that they take in. Okay, so find complete graphs of the cost and the revenue. Now, revenue isn't necessarily profit. You have to make a certain amount of money for your revenue to start being profit. Revenue is just money you take in. But if your revenue isn't as high as your cost, then you're going to lose money. Okay, so let's start with the costs. So we're going to find the costs as a function of x. X is going to be the number of shirts that we make. Okay, it'll be the number of shirts. So how would we represent the cost just to make the shirts? Yeah?
Negative 1.5x?
So we want to write the cost as a positive number. Because we're going to think of the cost as just, it costs the company $100 a month.
1.5x.
Yeah, we won't want to say like it costs the company negative $100 a month to make shirts. Yeah, so it costs the company $1.50 per shirt. And what do we have to add to that to account for the fixed costs? Yeah. Yeah, and that's a fixed cost. You don't pay that for every shirt you make. Okay, so there's a graph, or there's an equation for the costs. Okay. Now let's do the revenue. Revenue is just money that they bring in. So let's say they bring all these shirts to like a flea market or something, and they start selling them, and they count the money in the register at the end of the day. That's the revenue. So how would you represent the revenue? Yeah.
4x.
4x. Yeah. It's just the money that's in the cash register at the end of the day. Now it says to find a graph. Okay. What's my y-intercept in the cost equation? How much? Yeah, Anthony?
200,000.
200,000. So when we set our window, I would probably go above that. Let's go like, we'll go 250,000. And as far as my cost or my revenue, I would never have what kind of number? Yeah, we're not going to pretend there's no negative cost, there's no negative revenue. So we don't need to look below 0. X is the number of shirts we make. What's the smallest number of shirts that we could decide to make? Yeah, you could make 0. Maybe you rent the building for $200,000 and you don't use it. Okay, so you didn't make any shirts. And the highest amount of shirts we could make, well, there's no limit. Let's say we make up to 50,000 shirts. And hit graph. I must have not set something, or I didn't put something in right.
I don't think we did put an equation in.
I didn't put the equations in. So put the equations in. 1.5x plus 200,000 and 4x. Okay, so there's our costs. And there's our revenue. And what do you notice is starting to happen the more shirts we sell? What's starting to happen? Yeah.
They're starting to head towards each other.
Yeah, the revenue is catching up to the cost because we're selling shirts for more than it costs to make them. So the 4x slope is eventually going to surpass the 1.5x. We should find that point on the screen. So let's double the number of shirts to 100,000 shirts. Okay, well, it's better, but what do I need to set higher now?
The Y max.
Yeah, I would set the Y max higher. Let's go, I don't know, let's try 400,000. Okay, so that, I think that'll be good. There's my costs. There's my revenue. Yep, that's good. So as far as finding a complete graph that shows that, I would say that's a good window. And the graph itself, right there. Just move that so you can see the original problem. There. Okay, so any question on the cost or revenue? So this point actually has a special name when you're looking at a graph of cost and revenue. Does anybody know what that point's called? Where your revenue finally goes past your cost? Yeah?
Isn't it where you break even?
Yeah, that's the break-even point, exactly. So it's the point at which the cost and the revenue are the same. And I already pointed this out to you. It's the intersection point on the graph. So the break-even point is when the cost equals the revenue, and graphically, it's where those two cross each other. So what we're going to do is we're going to solve, in our problem, for the break-even point. So find the number of shirts that the company has to sell to break even. First, I'm going to do it algebraically. And then I'll do it graphically. And I think that'll be the last, yeah, that's it in that section. That's all that was left. Does everybody have that part? That it's the intersection point? Okay. So find the number of shirts the company must sell to break even. Okay, so remind me again, what's the break-even point? It's where the cost is equal to the revenue. So all you have to do is look up your formula for each one of those. Costs were $1.50x plus 200,000. Revenue was 4x. And solve. So when we bring the 1.5 to the other side, what will I have on the right side? Yeah.
2.5.
Yep, 2.5x. And my last step to get x by itself?
Divide everything by 2.5.
Yep, divide everything by 2.5. So that's going to come out to, divide by 2.5, that's 80,000. 200,000 divided by 2.5. You can double check me if you want. That's 80,000. So if you sell 80,000 shirts, you won't have made money or lost money. You'll break even. Now you're at $0 in profit. Now let's do the same thing graphically. We're basically like 75% done the problem to do it graphically. We've already typed in y1 and y2. We've already set the window. Does anybody remember what we press to see where those cross? Yeah.
Second then graph.
Second and then trace. Yeah, second and then trace. And which option do we pick there? Yeah.
5.
5. Okay, it's going to ask me 3 questions. You're going to pick a point somewhere on the first line, hit enter. Somewhere on the second line, hit enter. And then the guess, well, how many times do these lines cross? Just one, so the guess doesn't really matter. I can put it right there, that's fine. All right, let's take that. And graphically, we get exactly the same answer as when we did it algebraically. 80,000 shirts. Now, if I make 80,000 shirts, how much will it cost me based on that graph? Yep.
$320,000.
It's going to cost me $320,000 to make 80,000 shirts. How much revenue will I have if I make 80,000 shirts?
320,000.
I'll have the same amount, $320,000. Yep. And that's all that was left in that section. Okay, so it's finding a break-even point. Any question on that? Okay, any question on using the calculator? Which buttons to press?
After you get like this quick option 5,
Yep.
you pick the 2 lines and then it'll.
Pick the 2, you pick the first line, hit enter, second line, hit enter, and then the yes, then hit enter.
Yes, okay, got it.
Yep. All right, so what we'll really focus the rest of today on is solving linear and quadratic equations. Hopefully everything in this section should be reviewed from Algebra 1. Before we can talk about solving an equation, we got to just talk about what is an equation. Is this an equation? 2x plus 3? What do you think? Yeah, go ahead, Meg.
It's not, because there's no equal signs.
Yeah, there's no equal sign. Okay, once I put an equal sign in there, now it's an equation. So an equal sign has to have, an equation has to have an equal sign. So you have to have an expression on the left, an expression on the right, and an equal sign between the two. No equal sign, no equation. So if I ask you to solve an equation, it means to find the value or values that make the equation true. So if I was going to take 2x plus 3 equals 5, and I said to solve it, you would minus the 3 from both sides, divide by 2, and you get x equals 1. So that's, when I ask you to solve an equation, that's what I'm looking for you to do. Now, some equations, when you solve them, it ends up with all real numbers as the answer. If that happens, that type of equation is called an identity. The one that I did up above that I just solved and got x equals 1, that's not an identity. There's only one number that makes that equation true, the number 1. But this equation right here, 3x plus 2 equals 3 times x plus 1 minus 1, with the x plus 1 in parentheses. This is going to be an identity. Let's see what happens. What would be my first step to solve that equation? Yeah?
Distribution.
Yep, so we're going to distribute, and when you distribute the 3, what do you get?
3x plus 3.
Anything else on that side?
Minus 1.
Yep, and the minus 1. So you have 3x plus 2 equals. And if you simplify by combining like terms on the right, What do you have on the right? Yeah,
3x plus 2.
right. And now some people might not notice anything and they say, oh, put all the x's on the same side. So if you did that, you could minus 3x from each side. That's gone. And that's gone. But at this point, you end up with 2 equals 2. All the x's are gone. That's an identity. It's a true statement, which means that you can plug in any number for x in the original problem, and it will always work. Because the x's don't matter. They end up canceling out anyway. So that's an example of an equation that's an identity. Bless you. Okay, versus something like a conditional equation. That's an equation that is true under the right condition. That means you have to let x be a certain number, or maybe numbers. So like in this case, what's the condition here that would make x? What's the number you would plug in for x that would make that equation true? Yeah? 5, yeah. So that's called a conditional equation because there is a condition on the variable that has to be met for it to work. In this case, the condition is it has to be the number 5. So any question on the difference between an identity and a conditional equation? So one thing that I might ask you to do is, once you get a number as a solution, I want you to check it or verify it. To verify that something is a solution, you take the number that you found, or the number that you're given, and you plug it back into the original problem for the variable, and see if you get a true statement. So, if I want to verify that -2 is a solution to this problem, when I plug -2 back in where I just circled, what do I hope to get?
0.
I hope to get 0 because I need to get the same thing that's on the other side for it to be a true statement. Okay, so let's plug in -2. I'm going to put a question mark there because I don't know yet if plugging in -2 will give me 0. That's the hope. -2 cubed is going to give me, yeah, -8. And -2, what does that become? Yep. Yep, becomes +2. All right, and what's -8 plus 2? -6 plus 6.
0.
Perfect. So I ended up with a true statement, which means what about -2?
It's a solution.
It's a solution. -2 is a solution. And to verify that, you just have to show me the steps that we did right there. Any question on verifying a number as a solution? All right, so now we're going to talk about 2 types of equations. We're going to do linear first, and we'll do quadratic second. So a linear equation is an equation that can be rearranged to look like that. Something times x plus a number equals 0. So this is a linear equation. And it's exactly in the format that it needs to be. How about this one? Is that one exactly in the format right here? No. Could it be rearranged to be in that format?
Yes.
Yes. You could minus the 4x and you could add the 7, put everything on one side, and you would have something that looks exactly like ax plus b equals 0. All right, so a linear equation basically has only x's to the first power. If you have an x to the second power, it becomes something else. Okay, but you can only have x's to the first power. Okay, so look at this equation. Would it be possible to do all this out and rearrange that equation so it looks like what's in that box? Is this a linear equation? What do you think, Martin?
Yes.
Yeah, it's a linear equation if you do it all out. It only has x's to the first power, so you could get it equal to 0. We generally don't get it equal to 0 when we're trying to solve it. That's just the definition of a linear equation. That if it was equal to 0 on the right, it would look like that on the left. Okay. All right, so what's my first step on the left-hand side? Yep.
Distribute.
Yep, I'm gonna have to distribute. And what am I distributing in the first parenthesis?
2x and -3.
So yeah, the 2, and can you tell me, Martine, what I get when I do that?
4x minus 6.
Okay. And somebody else tell me what I get for the next part. Yeah,
3x
Anthony?
plus
3x plus 3. Perfect. So not an equation I would start out with in Algebra 1, but I'm hoping you guys are pretty comfortable with distributive property at this point. Okay, next step. Yeah.
Subtract the 5x and the negative 2 from the right side.
Something else I would do first to simplify something we have there. Yeah?
Would you just add the 3x to the 4x?
Okay, we can add the 3x and the 4x.
Add the 3 to the negative 6.
Oh, yeah, sorry, yeah. Add the 3 and the negative 6. So we get minus 3. So that's good. Combine our like terms. And if we wanted to make it look like that format, we could. We could put everything on one side, it would equal 0, and it would be linear. But we're trying to solve it for x. So we don't want to get 0 on one side, we want to get x on one side. So what would be my next step to start to get all the x's on one side? Yeah, Ben?
Would you add the 3 to?
Yep, we could add the 3 on both sides. That's gone. And what else could I do in the same step? Just saves me from having to write this a second time. Yep.
Subtract the 5x from both sides.
Yeah, so let's handle all that at once. So I have 2x equals 5. And now, as we said before, you could do 2x and then make it minus 5 equals 0, and it fits the pattern of a linear equation. But we don't want it equal to 0. We want x alone. So what's my last step? Yeah.
Division.
Yep. And what would you divide by?
2.
Perfect. So x equals 5 halves. If they don't ask for a decimal, we'll just leave it 5 halves. Okay. Any question on solving that equation? All right. So the next application we're going to look at is absolute value, and that's going to split into 2 problems. Okay, so we're going to have 2 equations to solve. So to solve an absolute value problem, the first thing we have to do is isolate the absolute value. Okay, what do I mean by that? Here's an example where the absolute, I'm not going to solve this problem, I'm just showing you an example. The absolute value is isolated on the left because there's nothing else outside the bars. Here's an example where the absolute value is not isolated. There's something else outside the bars on the same side. So the first thing we would have to do is get this alone on one side. If this was the problem we were going to do, how would you get what's in that red box alone on one side? Yeah.
Minus 3 on both sides.
Yep, you'd have to minus 3 on both sides. And again, I'm not going to do that, but that would be your first step. Now, if we had, let's just say, you have this problem. There are two answers to that problem. What number can you take the absolute value of? Not what do you plug in for x. What number can you take the absolute value of? And it comes out to 12. Yep?
Negative 12.
Negative 12. Or
12.
12. So what's inside here can either come out to 12 or negative 12. And it will satisfy that equation. So in that case, the numbers would be 4 or negative 4. Yep?
Oh, you're gonna say that.
Oh, you're going to say it, yeah. So there's two answers. So now I'm going to show you how we split that up into two problems, because you might not always be able to guess the answer so easy. Okay, the first problem that we split it up into is the exact same problem, you just take away the bars. Just like that. The second problem we split it up into is we take away the bars and we change the sign of the number on the other side. So if you didn't know the answer, that's how you would split up this problem to solve it. What's inside the bars equals 12, and what's inside the bars equals the opposite of 12. So negate just means change the sign of, just a shorter way to say it. Let's try this one. So the first question, oops, is the absolute value already isolated?
Yes.
Yeah. We just got an absolute value of 2x plus 3. There's nothing else outside the bars on the same side. So we're just going to split it up. Can anyone give me the first equation that that's going to split up into? Yep.
2x plus 3 equals 5.
5. And the second equation? Yeah.
2x plus 3 equals negative 5.
Perfect. And now you solve each linear equation just like we did at the beginning. So we're going to get 2x equals 2 by subtracting the 3 from both sides. And we end up with x equals what for my first answer? 1. X equals 1. And over here, we're going to get 2x equals negative 8 when you subtract 3 from both sides. And when you divide by 2, x equals negative 4. And technically, the word or is between those answers. Yeah.
Can we use the U symbol too, or?
That symbol is usually used when you're dealing with sets, like intervals. Since these are just single values, I haven't seen that notation used with the way I wrote this answer.
Oh.
Yeah. Okay. Now, absolute value is always equal to what kind of number? It's always equal to a positive, yes. Okay, so we know absolute value is always equal to a positive. So what if I wrote this? What do you think the solutions would be to that problem? Yeah, Gracie?
4x minus 5 equals negative
So 4x minus 5 equals negative 8, and 4x minus 5 equals negative 8. All right, let's just solve one of them and see what happens. So we get 4x equals, if you add 5 to both sides, negative 8 plus 5 is negative 3. And divide by 4. You get x equals, whoops, that was not a negative. Divide by 4, 4. X equals negative 3/4. Well, plug that back in and see what happens. It doesn't even matter what I plug back in, because when I plug in negative 3/4 here, multiply it by 4, and then minus 5 from it, and take the absolute value, I'm guaranteed when I take the absolute value that I am not going to get what kind of number? You're not going to get a negative answer when you take the absolute value of something. So that's not going to work. So what do you think the answer would be in this one? Yeah?
One with a positive 8.
Okay. Oh, I didn't even write it as a positive 8. I should have. But even if I plug in that one, if I multiply a positive times, if I plug in a positive number here, right, because this would end up being positive 8 plus 5 is 13 over 4. Positive times a positive is a positive. Minus 5, well, maybe it's a positive or a negative, but I'm going to take the absolute value of it. Yeah?
No solution.
Yeah, this doesn't have a solution. You can't solve absolute value equal to a negative number. You can set it up and you can do it. You'll get answers, but they won't work. Now, what if I had this? Would we still just look at that and say, oh, absolute value, negative number, can't solve it? No, why is this one solvable? Yeah.
Because you have to isolate the absolute value and add 10 to the negative 8, so that makes the negative 8 a positive 2.
Right. So when you're solving this one, when you get the absolute value by itself by adding 10, it's not going to be a negative anymore, and that's okay. All right. So any questions on solving absolute value equations?
So why would it have no solution again?
This one that we
Yeah.
did well before I changed it?
Yeah.
Because you can't take the absolute value of a number and have it equal a negative. If you were to graph an absolute value, it looks like a V shape. In that last problem, you'd essentially be asking, where does the V shape cross negative 8? And it would be something like that. The V shape would never cross negative 8. It wouldn't go low enough. Yep. So let's look at, I think this is the last application of linear, and then we're going to finish up with quadratic. A mixture problem. So to do a mixture problem, you're going to have to set up two equations. So to solve a mixture problem, you're going to need two equations. And just to give you an idea of what we're going to do, we're going to have two solutions we're going to mix together. So let's use like rubbing alcohol as an example. Let's say you had a bottle of 70% rubbing alcohol and 90%. Okay, two different strengths. And I want you to mix the two together so that you have 86%, which is doable because you got a 70 and you got a 90. So you're going to mix them together to make 86%. And when you're done, I need 10 gallons of it. So you need 10 gallons of 86%. Tell me how much of each one you need to mix together. So one equation that you need to set up is for the total amount. Right? So we don't know how much of the 70%, we don't know how much of the 90%, but we know added together, it's going to be a total of 10 gallons. Okay? And the other equation is going to take into account the concentrations. So this one will be for like our first solution. It's the concentration of that solution times how much we're going to use. That's going to be for my second solution. That's going to be the concentration of that solution times how much I use. And the third part that's on the other side, that's going to be my, we'll call it the final mixture. That's going to be the final concentration times the total amount of liquid I need. So I forget, I know I said I wanted 10 gallons, and maybe I said 86%. So one thing we have to remember about the concentration is it needs to be a decimal. Hi. Yeah, can you come back? Thanks. So the concentration has to be a decimal. So that means if you had a percentage of like 15%, what's 15% as a decimal? Yeah? 0.15. Yep. So you got one equation for the amount, and then you got one equation for the concentrations. Okay, so let's set it up and see if we can solve the mixture problem. Okay, those are the two equations you'll need to do it. Okay, so we have two different solutions. Let's call them solutions A and B. Since the two solutions are already named, I would use those as the letters in the problem. Then it'll be easy to remember which one is which. If I didn't have letters, I might use X and Y. But for this one, let A be the amount of this solution. So how much of the first solution are we going to use? We're going to use A. Liters or gallons, they'll tell us in a minute. So let A be the amount of this solution. And then for solution B, I would let the letter B be the variable that represents how much of that one you're going to pour in. So let B be the amount that you use of that solution. So when we're done mixing the two together, we want to get 15 liters. And we want it to be a 12% solution. The percentage here has to be a number between those two. Can't be outside those two. Okay. So how much of each solution do we need? Okay, so first step. Let's set up our amount 1 plus amount 2 equals the total. How are we representing the amount that we need for the first solution? This is amount 1. Yeah? A. How are we representing how much we need for the second solution? This is going to be amount 2. Field trip one?
Yeah.
Yeah, can you just come back? I won't be teaching at like 12:05. Yeah. B. So the amount of the first solution is A. So anywhere you see an amount 1, we're changed to A. Amount 2, we're changing to B. And the total amount, well, that was given. What's the total amount that they want us to make? Yeah.
15 liters.
15 liters. Okay, so there is your first equation. That's not enough to solve it, because there's a lot of answers. I could let A be 1 and let B be 14. A could be 5, B could be 10. But that wouldn't give me the right concentration, right percentage. That's going to be my second one. So we need concentration times amount, concentration times amount, concentration times amount. This is for solution A. That one is for solution B. And this is the final mixture. Okay, so we need concentration times amount for each one. What's the concentration as a decimal for solution A? Yeah, 0.1. And what's the amount of the first solution that we need to use?
Do we not know that one?
We don't have a number for it, no. Yeah?
A.
A. Okay, now the second solution we're going to pour in. What's the concentration for the second solution? Yep,
0.25
0.25. And how much of that solution do we need?
B.
B. And now the final mixture. What's the concentration that the final mixture has to be? Yeah.
0.12.
Yep, it's going to be 0.12. So that's the final concentration times the total amount of liquid in the final mixture. What's the total amount of liquid? Yeah,
15.
15. Okay, so we can simplify that a little bit. We're going to want to multiply the two numbers under the final mixture together. But that's all we can really do. So we've got 0.1A plus 0.25B. And what's 0.12 times 15? Yeah. 1 point what? 1.8. Okay. So in that box, that is equation 2. Okay, so now what we have is a system of equations. We've got two equations. Each equation has two letters in it. Does anybody remember one way that you can solve a system? Yeah? Yep, substitution. There's different ways. Substitution is a pretty good way for this one. You need to pick one of these equations and get a letter by itself. Which equation do you think is easier to get a letter alone? The top or the bottom? Yeah?
Top.
Yeah, I would say the top. It's a lot easier to get a letter by itself. And what letter do you want to get by itself there, Tom?
Go with A.
Go with A? Can you tell me if you get A by itself, what would be in that box?
Negative B plus 15.
Negative B plus 15? Yep. Or you could also just think of it as 15 minus B. Negative B plus 15 is the same thing. Okay, so that's your first step with substitution. Now, what do I do with that 15 minus B? Yeah.
Plug it into A in the second equation.
Plug it in for A in the second equation. Yep. All right, so let's do that. We've got 0.1 times, we're going to fill in for A, 15 minus B, plus 0.25B equals 1.8. Now we have an equation that only has one different letter in it. That letter appears more than once. We need to fix that. But it's just one type of letter, just a B. Okay, Olivia, what am I going to do with this 0.1? Yep. 0.1 times 15, just like 15 divided by 10. So it's 1.5 minus 0.1b plus 0.25b equals 1.8. Next thing I can do, combine like terms. What do I get when I combine my b's together? Negative 0.1 plus 0.25.
0.15.
Yeah.
One, yeah.
Positive 0.15. Okay, so now we've got B all combined. What would be my next step to start getting B by itself? Yep.
Subtract 1.5.
So subtract. You get 0.15B equals, what's 1.8 minus 1.5?
1.3.
Uh,
Wait, 0.3.
0.30, yeah. And the last step, divide by 0.15. If you want to think of that without decimals, it's like 30 divided by 15. It's the same problem. Which would give me how much? Yeah, 2. So now I know I need to mix in 2 liters of solution B. How many liters of solution A do I need? Yeah.
Plug that in the first equation, so you need 13.
All right, and that's how much?
13.
13. 15 minus, now I know B is 2. So A is 13 liters. And that's pretty much how a mixture problem is every time. Those are the steps you need to do. Okay, any question on that? That was our final linear type of problem. Then we're going to look at quadratics real quick.
I'm going to write this down. After that, could you go back to the first equation that you made?
The first equation?
Like the concentration times the amount and that one.
Yep. So these were all linear because when you looked at the variable, the highest exponent on every variable was always what number? Even though we didn't write the exponent because it was a 1. Yeah. If you don't write the exponent, it's a 1. So now we're going to look at some equations that have an exponent of 2. It's not linear anymore. Does anybody know what we call it when it has an exponent of 2? Yeah? Quadratic. Perfect. Yep. So let's take a look at quadratic. So quadratic equations have that format. Ax squared plus bx plus c. It's very common to use the a, the b, and the c to represent the number in front of the x squared, the number in front of the x, and the number that doesn't have the x at the end, which is the constant. Now, the only thing, you can let a, b, and c be any numbers that you want, positives, negatives, fractions, decimals, 0. Except for a, there's one number that a can't be, and that's 0. What would happen if you filled in a 0 for the a? Yeah?
It would technically just be linear.
Then it would just be linear, because if you fill in a 0 for a, 0 times x squared is 0, you'd wipe out that first term, and you'd have something times x plus a constant equals 0. That's exactly what we said linear was. Something times x plus a constant equals 0. So you can't wipe out that first term. Then it wouldn't be quadratic. So one way to solve a quadratic is to take it and factor it. What factoring does is it turns something that has an exponent of 2 into 2 problems that have exponents of 1. So that's always the goal, to get it down to linear, then we can solve it. And factoring is one way to do it. Unfortunately, it only works when the numbers are nice. Okay, but I'm going to give you ones. If I ask you to factor it, then it will be factorable. So let's try this one. So to factor it, we need to start out with 2 sets of parentheses. And what we want to put for the first term here and the first term here, 2 things that would multiply together to give me 2x to the second power. What would be 2 things I could multiply together to get 2x to the second? Yeah?
X times 2x.
X times 2x. Yep, so 2x and x. That's perfect. Now we need the signs in the middle. They're either both positive, both negative, or one of each. And that tells you what you need to put down below. You don't always just copy them. You have to look at it and kind of analyze it. You have a positive in the middle, and you have a negative for your constant. What does that mean you need when you factor? Yeah.
One positive, one negative.
Right, you're going to need one positive and you're going to need one negative. Because in a minute, you're going to have to multiply something times something to get -3. If you had a positive and a positive, could you multiply those together to get -3? No. If you had a negative times a negative, would that give you -3? No. Negative times negative is positive. So to get a negative, you need one of each. Yeah.
Does it matter the order that we put the plus or minus?
It does on this one because these two things are different. So if you accidentally switch them, we're either going to get a -5 or a +5. We want a +5, so that's why I put them the way I did. If I had put the positive first, we would have gotten a negative in the middle. You'll see in a second. Okay, now I need two numbers that multiply to give me 3. I've already taken care of the negative. Negative times positive is negative. Just two numbers that multiply to give me 3. Yeah?
1 and 3.
And I'll put them in the order that you said because it works. That's the right order. Okay, let's check it. 2x times x is 2x squared. What's 2x times 3?
6.
6x.
X.
And what's x times -1?
Negative X.
And 6x take away 1x?
5X.
5x, perfect. So I was foiling it out to check the answer. Okay, now that we factored it, you took something that had an exponent of 2 and you turned it into two problems, two factors, and they each have exponents of 1. So now, set each factor equal to 0 and solve. So take your first factor, 2x minus 1, set it equal to 0. Take your second factor, set it equal to 0, and solve. What would I get for x when I get it by itself in that first problem? Yep.
1/2.
Good, 1/2. And what would I get for x when I get it by itself in that second problem? Yeah,
-3.
-3. So most of the time, or a lot of the time, quadratic equations will have two answers. Two, let me put it this way, real answers. Is there any question on that? Yeah.
Do we have to factor it like how we did it, or can we do it where we split bx into 2 terms?
Can you say that again? Where you split what?
Or you split bx into 2 terms, and then you factor it out that way? Like turn it into 4 terms and then factor it out.
Okay, yeah, you'll have to show me that method. Maybe it's just something either I don't quite understand, or maybe it's something I haven't done before. Yeah, I'd like to see that after. So yeah, there might be other ways to factor it. But yeah, let me take a look. All right, any other questions on that? Yeah.
In the first set of parentheses, why'd you put a 2x and an x there again?
The 2x, because you have to find, if you were to FOIL it, something times something that gives you 2x squared.
Okay, and that goes for everything that looks like that in an equation?
Yeah, whatever you put here times whatever you put here has to give you what's there.
Okay, got it.
Yeah. And whatever you put here times whatever you put here has to give you what's there. But then the middle is the trick. You have to somehow also get the number in the middle.
Okay.
Which is why if you switch the signs, it wouldn't work. You would end up with -5 in the middle.
Okay.
So now factoring is great as long as you can factor it. Does anybody remember the last way that you can, or another way you can solve a quadratic if you can't factor it? Yep.
Quadratic equation?
Yeah, the quadratic equation or the quadratic formula. Okay, so if you are unable to factor the problem, then we'll use this formula. Okay, so we'll do one with the quadratic formula, and then that'll be our last one. So the quadratic formula is what has 3 letters in it, A, B, and C. And just to be clear about where those letters are coming from, the A is the number in front of x squared, B is the number in front of x, and C is the constant at the end of the equation. So it's the opposite of B, plus or minus. That's where you get the 2 answers. So when we factor, we split it into 2 problems. When we use quadratic formula, we do plus or minus. Square root of, and then under the square root, b squared minus 4ac, that is called the discriminant. It's the part of the quadratic formula that's under the square root. It's just the name of it. And then the entire thing is divided by 2 times a. All right, so in order to use that formula, we need to make sure that it's equal to 0. If you have an equation that is not equal to 0, then we need to fix it so that it is. I also want to make sure I give you a problem that's going to work, so that's why I changed the numbers. Okay, so let's look at example 6. Is that equal to what it should be if we're getting ready to use quadratic formula? No. In fact, even if you're going to factor, I didn't say it here, but it does have to be equal to 0. I didn't mention it on the last one because it already was. Okay, but anytime you solve a quadratic, it has to equal 0 first. Okay, so can somebody tell me what I would do to get this equal to 0? Yeah.
Just subtract 1.
Just subtract 1. So 2x squared plus 5x minus 1. Okay, now just make sure we know what's what. What's a going to be when we fill in?
2.
Yep, a is 2. And b?
5.
B is 5. And c?
So 1.
What is it?
The 1. Or the negative 1.
Negative 1. Yep. Okay. Can anybody start to set up quadratic formula for me using those 3 values? What's the first thing I would put down? Yeah.
-5
Negative 5. Yep.
plus or minus the square root of 5 to the second power.
And let's do that out just so we have that done. What's 5 to the second power?
25
25. Okay, looks good so far.
minus 4 times 2 times -1,
Negative 1.
and then divided by 2 times 2.
2 times 2, which is? Perfect. Okay, so I'm just going to solve it on the left because I got some more space over here. Okay, so now we've got -5 plus or minus square root of 25 minus, what's 4 times 2 times -1?
Negative 8.
-8. So we really have minus a minus under the root. So what's going to happen with that?
Addition.
That's going to become addition. then 25 plus 8,
33.
33. And if they want an exact answer, well, that's all you can do. That's the final answer. Negative 5 plus root 33 over 4, and negative 5 minus root 33 over 4. Now, let's say, in this one, this didn't happen. Well, let's say the root came out to like square root of 20. How can you break up 20 into two numbers that you can take the square root of one of them in your head? Yeah? 4 and 5. So if you get a square root that can be simplified, you need to break that square root down as much as you can. Again, 33 you can't, so you're done. But I'm just showing that as an example. Okay. Any question on that? All right. Okay, so that covers everything in that half section we didn't finish, and then the other section. So page 89, 35 to 39, that is a break-even point problem. I think it's like find the cost, find the revenue, find the graph, find the break-even point. So it's all one question. And then page 96, that's on solving linear and quadratic equations. Okay, just a reminder again, I will be after school on Thursday if anybody needs to stop by for extra help. Progress report's closed Friday, so I'll be doing your homework averages, updating all that stuff on Friday. And this test will be part of progress reports, and it will be our third test for the term so far.